Welcome to the listening section of the TOEFL mock test, brought to you by Spinta. This section measures your ability to understand conversations and lectures in English. In this section, you will listen to several conversations and academic lectures. Each conversation and lecture is followed by a number of questions. You will hear each conversation or lecture only one time. You may take notes while you listen. You may use your notes to help you answer the questions. Some of the questions will replay part of the audio for you. Answer the questions based on what is stated or implied by the speakers. You must answer each question before moving on. You cannot return to previous questions in this section.
Good morning. Today I want to talk about permafrost thaw and the climate feedbacks that arise when frozen soils release greenhouse gases. This is an area of active research because it links physical change in the Arctic and subarctic to global climate trajectories. First, I will define permafrost. Permafrost refers to ground that remains at or below 0 degrees Celsius for at least 2 consecutive years. It stores large quantities of organic carbon because plant material has been frozen and protected from decomposition for millennia. Estimates suggest that northern permafrost soils contain roughly twice the amount of carbon that is currently in the atmosphere. When permafrost thaws, microbes become active and decompose the organic matter. The exact pathway of decomposition depends on whether conditions are aerobic or anaerobic. Under aerobic conditions, carbon is released mainly as carbon dioxide. Under anaerobic conditions, such as waterlogged soils and drained or subsiding ground, microbes produce methane, which is a much more potent greenhouse gas per molecule over short time horizons. There are two important thaw processes to distinguish. The first is gradual deepening of the active layer, the seasonally thawed surface soil. This process increases decomposition rates slowly as more organic matter becomes available to microbes each summer. The second process is abrupt thaw, which includes thermokarst formation and ice wedge collapse. Abrupt thaw can expose deeply frozen organic carbon suddenly and create anaerobic ponds that emit large pulses of methane. To illustrate, consider the so-called Yudoma deposits in northeastern Siberia. Yudoma are ice-rich deposits with high carbon density. When they collapse, large quantities of previously stabilized carbon are suddenly exposed. Field observations and remote sensing have documented localized hotspots where abrupt thaw has led to rapid landscape change and strong greenhouse gas emissions. This brings us to feedbacks. A positive feedback occurs when warming causes permafrost thaw, which releases greenhouse gases, which then cause further warming. If permafrost emissions are significant, they could reduce the carbon budget available to meet temperature targets, such as the targets set in international agreements. Modeling these feedbacks is challenging. Many Earth system models include permafrost carbon as a gradual response, but they may not capture abrupt thaw processes or the full spectrum of methane production. Observational constraints are improving, however. Long-term monitoring networks, flux towers, and new satellite measurements of surface subsidence and thermokarst help to identify where emissions are concentrated. There is also a strong socioeconomic component. In parts of Alaska and Russia, thawing permafrost damages infrastructure. Roads crack, buildings settle, and pipelines lose support. This raises adaptation costs and also underscores that permafrost change has both local and global consequences. Let me give you a recent case study. After an unusually warm summer, researchers measured a sudden increase in methane flux from a Siberian thermokarst lake. The site had experienced thaw slumping the previous year, exposing deep organic layers. Methane emissions persisted for months and were detectable by aircraft and satellite instruments. That event highlighted how local abrupt thaw can produce emissions that matter at larger scales. From a policy perspective, the existence of permafrost carbon feedbacks implies that emission reduction targets should account for these additional sources. It also motivates investment in mitigation strategies such as protecting carbon-rich peatlands, reducing other greenhouse gas emissions to limit warming, and improving monitoring to refine model predictions. To summarize, permafrost stores vast amounts of carbon. Thawing can release that carbon as carbon dioxide or methane depending on conditions. Both gradual active layer deepening and abrupt thaw processes are important. Improved observation and inclusion of these processes in models are essential to predict future climate trajectories and to inform policy. If permafrost thaws more rapidly than models predict, then we could see a significant additional source of greenhouse gases that will amplify warming. That concludes the main points. Next class, we will look closely at measurement techniques and how isotopic analysis helps distinguish sources of greenhouse gases in Arctic regions.
Listen again to part of the lecture, then answer the question.
If permafrost thaws more rapidly than models predict, then we could see a significant additional source of greenhouse gases that will amplify warming.
For more TOEFL mock tests, as well as IELTS and Cambridge practice, visit www.spinta.org. We provide updated tests every single day, AI feedback for your speaking and writing responses, and access to a wide range of high-quality mock tests to help you prepare with confidence.